Since we are done with Bravais lattices, now let us talk about how to find the number of atoms in a unit cell. How to find the number of atoms in a unit cell. We have seen that unit cell can be classified as primitive cubic unit cell and centered cubic unit cell, and centered cubic unit cell can be further classified as body centered cubic unit cell and face centered cubic unit cell, and there was a third classification of centered cubic unit cell, that was face centered cubic unit cell, end centered cubic unit cell. So when we want to find the number of atoms in a unit cell, we'll see about the first primitive cubic unit cell. If you remember, in primitive cubic unit cell, at the corners only of that cube, atoms or the constituent particles were placed, and at no other different position than corner, atoms or that constituent particles were placed. Now these are three different ways of representing primitive cubic unit cell. This is open structure, and this is a space filling structure, and this diagram is actually the actual portions of atoms in that primitive cubic unit cell. To better understand that, let us take some spheres. Suppose if I take these spheres, okay, I hope you can see these are 8 spheres, and if you join the centers of each sphere, the actual primitive cubic unit cell, which is drawn over here on the board, will become like this. Correct? If you see this structure of 8 balls, actually if you join the centers of each sphere, then it will be a primitive cubic unit cell, and that is why if you see this space filling structure, it looks like the same which I hold in my hand. These are 8 spheres placed at the corners of a cube, and that is what a primitive cubic unit cell is. Correct? Now let us find the number of atoms in a primitive cubic unit cell. Now if you see this structure where we have drawn the actual portions of atoms, the sphere at each corner is shared by 8 different cubes. The sphere or the constituent particle placed at a corner is shared by 8 adjacent cubes. So it means inside this cube, that will be only 1/8 portion of each sphere placed at each corner. Correct? So if you want to find the number of atoms, we can say that since there are 8 corners in a cube, and at each corner an atom is placed, and only 1/8 portion of that atom is inside this cube, rest is shared by 7 different adjacent cubes. It means since we have 8 different corners and only 1/8 of a particular corner or the atom at a corner is coming inside this cube, the number of atoms will be 8 into 1/8, that is 1 atom only. So effectively, if you join all these pieces, 1/8 of each sphere, each atom placed at each corner, effectively it will turn out to be into 1 atom. If you join all these pieces together, it will be 1 atom. Why? Because this sphere, the atom at each corner is shared by 8 different adjacent cubes. So the portion inside one cube will be only 1/8. Since we have 8 different corners in a cube, so the effective number of sphere or the atom inside this cube will be 8 into 1/8, that is 1 atom. Now if we talk about the centered cubic unit cell, and the first classification of centered cubic unit cell, that is body centered cubic unit cell, these are the different diagrams, structures which we can draw, where if you see this open structure, at each corner there is an atom, and also at the center of this body or the center of this cube there is an atom. Correct? If you see these yellow circles, at each corner there are different atoms, and also there is an atom exactly inside the cube or the body of this body centered cubic unit cell. Similarly, if you see this space filling structure, there are 8 different spheres, and between that a single sphere has been placed. So if you want to understand this with the help of spheres, we can say if you see this structure carefully, you will find that the external 8 spheres which are which my hand touches, the external 8 spheres are the corners, and inside this particular structure there is an atom or sphere. Correct? So this is what a body-centered cubic unit cell actually looks like. At the center of this cube, if you join the centers of each sphere placed at the corners, it will become a cube. Correct? And if you see at the center of this cube, there is a sphere placed, and that is what a body-centered cubic unit cell looks like. If you see this space filling structure, it is actually this way. There are four different 1, 2, 3, 4, and these 4 spheres. There are 8 spheres at each corner, one sphere at each corner of the cube. If you join the center of each sphere, it will become a cube, and exactly one atom or sphere has been placed inside this cube or the body. That is what space filling structure looks like. Now if you see this structure, inside this cube, one atom has been placed exactly at the center of the cube, correct? So this atom completely comes inside this cube, whereas like in primitive cubic unit cell, only 1/8 portion of each sphere placed at the corner was coming inside this cube, correct? So if you talk about body-centered cubic unit cell, there is one atom exactly inside this cube, and 1/8 portion of each sphere placed at the corner will be inside this cube, and rest of the part of the corners, spheres placed at the corners will be coming at the adjacent cubes. So once again, if you talk about body-centered cubic unit cell, 1/8 from each corner, 1/8 of atom from each corner is coming inside this cube, and there is exactly one atom placed inside this cube, correct? So if you want to try to find the number of atoms, in a body-centered cubic unit cell, we can say that number of atoms is equal to, I've just shown you using those spheres, 1/8 of atoms placed at corners is coming inside this cube, and there are 8 different corners, similarly as we have done in primitive cubic unit cell. So from corners the contribution comes as 8 into 1/8, correct? That will turn out to be 1, and there is exactly one atom placed at the center of this cube. It means plus 1. So 8 into 1/8 makes 1, plus 1 atom exactly at the center of the body. So number of atoms in a body-centered cubic unit cell will turn out to be 2. I hope you have seen that 3D view of spheres in my hand, which exactly becomes like this body-centered cubic unit cell if you place one atom between those 8 different spheres, correct? Now let us talk about the third type of unit cell, basically second classification of centered cubic unit cell, that is face-centered cubic unit cell. Now if you see these diagrams, this is how we have seen about face-centered cubic unit cell. At the corners, all the corners, there is one atom, and at the center of each face, of this cube, there is an atom, correct? This is the space filling structure which we will see with the yellow squares, and these are the actual portions coming inside the cube. Now similarly in we have talked about in primitive cubic unit cell, we have seen about body-centered cubic unit cell, that at the corners atoms are placed, and from each corner 1/8 portion of that atom come inside the this particular cube, correct? Now there is an atom placed at the center of each face in face-centered cubic unit cell, and exactly half of that comes inside the cube. Now since there are 6 faces and half of each atom placed at the center of the face comes inside this cube, so it means half plus half plus half plus half plus half, 6 times half. So 6 into half will be the part of atoms placed at the center of each face is coming inside this cube, plus 1/8 portion of atoms placed at each corner. So let us see the 3D view of this face centered cubic unit cell. Now we'll see about only one face. Suppose, see, if you see this structure, you can understand that it is a primitive cubic unit cell, correct? If you see this structure, this is a primitive cubic unit cell, correct? Why? Because if you join the center of each sphere, then it will become a cube, and there is a sphere or atom placed at the corner of each corner of this cube, correct? If you join the centers of each sphere, a cube will form, correct? And we can say that at the corners of this cube, at each corner of this cube, an atom has been placed. Now, since we are going to talk about face-centered unit cell, where along with these atoms placed at the corner of the cube, there is an atom placed at the center of each face. Suppose if I say I am going to consider this face, okay? Now, if I am going to consider one face, then there is an atom placed at the center of this face. Okay. Now this is just one face of the cube. Similarly, there will be like this, there will be a face like this, there will be a face like this, and there will be a face like this, above and below. So there will be 6 faces, and at the center of each face, there is a sphere or atom. Correct? Now, if you talk about the contributions of each sphere, doesn't matter placed at the corners or the center of the face, then if you talk about the contribution from corners, the contribution is same, 8 into 1/8. 1/8 of each atom placed at the corner is inside the cube, correct? So if we talk about number of atoms, we can say 8 into 1/8 from corners. Why? Because 1/8 of each atom placed at the corners is inside this cube, and since there are 8 different corners of a cube, we can say the contribution from corners is 8 into 1/8. That will become 1. Now there is an atom placed at the center of each face, and there are 6 different faces in a cube, and the contribution of atom at the center of each face is exactly half. It means half of that atom is inside the cube and half outside the cube. And since there are 6 different faces, we can say 6 into half is the contribution from each face, center of each face, which will turn out to be simply 1 plus 3, that is 4. So finally we can say that number of atoms in face-centered cubic unit cell is turning out to be 4. Why? Because the contribution of atoms by corners of this cube will be 1, and since an atom is placed at the center of each face, the contribution from face side becomes 6 into half, since half of each atom is inside this cube and half outside this cube. So 6 into half, that is 3. So number of atoms, effective number of atoms in a face-centered cubic unit cell is coming out to be 4. So we have talked about how to find the number of atoms in a cubic unit cell. We have seen about primitive cubic unit cell, since atoms are placed only at the corners of the cube. So the number of atoms, the effective number of atoms inside this cube will be 8 into 1/8. Why? Because 1/8 of each atom placed at the corner comes inside this cube, or is shared by 8 different cubes. So it means that if a particular atom at a corner is shared by 8 different cubes, then only 1/8 of this particular atom will come inside this cube. Since there are 8 different corners of a cube, we can say the effective number of atoms coming from this particular structure will be 8 into 1 by 8, that is 1. If we talk about centered cubic unit cell, we have seen only body centered cubic unit cell, that is BCC, and face centered cubic unit cell, that is FCC. Now, along with the corners, there is exactly one atom placed inside this body in body centered cubic unit cell. Since the contribution from corners is coming out to be 8 into 1 by 8, like we have seen in primitive cubic unit cell, and there is exactly one atom inside this cube at the center, we can say 8 into 1 by 8 is 1. We can say 1 plus 1, 2 will be the number of atoms inside this cube, effective number of atoms. Now, along with the corners in face centered cubic unit cell, along with the corners, since there is an atom exactly at the center of each face, and half of that atom at the center of face is coming inside this cube and half outside the cube, or in other words we can say that the atom placed at the center of each face can be shared by 2 cubes only. So half will come inside this cube and half in the above cube or in a different cube. Now, since there are 6 different faces, we can say the contribution from each face, or contribution from faces rather, will be 6 into half. Since half of each sphere is coming inside this cube, it will turn out to be 3. And along with that, there are spheres placed at the corners also, and spheres placed at the corners, atoms placed at the corners are shared by 8 different cubes. So the share of this particular cube of atom at each corner will be simply 1 by 8. And since there are 8 different corners, so effectively if we join those 1 by 8 portions, it will become 1 atom. So 1 plus 3, 3 coming from faces, 1 coming from corners, so 1 plus 3, that is 4. So effective number of atoms rather in face centered unit cell, face centered cubic unit cell, that is FCC, is 4. So we have just seen how to find the number of atoms in a unit cell. In primitive cubic unit cell, the number of atoms, effective number of atoms was coming out to be 1. Why? 8 into 1 by 8. Every atom placed at the corners of a cube is shared by 8 different cubes. So share of one single cube will become 1 by 8. And since there are 8 different corners, so 8 different atoms will be there at each corner of a cube. So effective numbers of spheres or atoms in a primitive cubic unit cell was coming out to be 8 into 1 by 8, that is 1. Effective number of atoms in body centered cubic unit cell was coming out to be 2, and effective number of atoms in a face centered cubic unit cell, that is FCC, was coming out to be 1 plus 3, that is 4. Now, we all know that constituent particles in solids are closely packed. Why? To minimize the vacant space, correct? So let us talk about close packed structures of solids. The first type of close packing is close packing in one dimension. Close packing in one dimension. If you see over here, this is the way how atoms have been arranged in one dimension. How? If I join the centers, of each sphere arranged in such a fashion, then it becomes a single axis. For example, say this becomes x-axis, and if I take this point as origin, then I can draw y-axis also. Now I can see the centers of each sphere arranged in such a fashion lies only on x-axis. I can say this type of close packing is in one dimension, correct? There is no y-coordinate for each sphere arranged in such a fashion. So this is close packing in one dimension. If I want to understand that, say in a physical manner, in a better manner, I can say the atoms are arranged in such a fashion, and this axis is x-axis, this axis is y-axis, and since the atoms are placed along x-axis only, or the centers of each sphere lies only on x-axis, we can say this is close packing in one dimension. Then what is close packing in two dimensions? There are two different ways where we can see close packing in two dimensions. If you see this first one, it is square close packing. We are talking about close packing in two dimensions. The first one which you see is square close packing. How? Let us see by these spheres. If suppose I say this is one dimension arrangement of spheres and the second dimension has been placed in this fashion, where the center of the second layer is exactly above the center of first layer. If you see the center of this particular sphere, if you see the center of this second layer placed above the first layer, you can say that center of each sphere in this second layer is exactly above the center of sphere in first layer. These are the spheres in first layer. This second layer, this is the second layer, and because of which it is becoming two dimension now, as y coordinates have been generated now. Earlier it was only along x axis, now it is building above y axis also, so it become two dimension, correct? Now the first way, that is square close packing. In that case, the spheres in second layer have centers exactly above the centers of first layer, correct? You can see that. So this becomes square close packing. Now the other way which you can see on the board written over here is hexagonal close packing. How? If these are the spheres along x-axis and it is only first layer, there is no second dimension, it is only one dimension close packing, correct? Now if I introduce the second layer in such a fashion that the center of second layer is not above the center of first layers but in between the voids of the spheres in first layer. If you see carefully, the centers of the second layer is now not above the centers of atoms of first layer. Why? Because it will become square close packing. This time the centers of atoms in second layer is exactly above the voids. Voids means the space, the gap between two consecutive atoms. The centers of atoms in second layer is exactly above the void or the space between two atoms in first layer, correct? If you see this way, you can say that now this there is no the centers of second layer does not coincide with the centers of first layer in a vertical line, correct? Or the centers of atoms in second layer is now not exactly above the centers of atoms in first layer, correct? You can see that. So this is hexagonal close packing, where the centers of atoms of second layer is not exactly above the centers of atoms in first layer. Had the centers of second layer, atoms of second layer, been above the centers of atoms in first layer like this, then it will become square close packing, and if I shift in this way, then it becomes hexagonal close packing. Now why this is two dimensional? Earlier if this was x-axis, the centers lie only on x-axis and it is one dimension. Now since I am going to introduce y-axis now by placing different layers above the first or second layer, so since I have introduced the second dimension, this is close packing in two dimensions. And like I said, if I place the centers of each layer exactly above the centers of atoms of the below layer like this, then it becomes square close packing. Okay, now let us understand that if I join the centers of atoms of first layer in such fashion and this becomes the y-axis, then you can say that this sort of packing is two-dimensional, and since the centers, if you see, if I mark the arrangement such that A, why A? This is because the centers of each layer above the below layer, the centers of atoms of each layer is exactly above the centers of atoms of the below layer. Such type of arrangement is also called as AA type of arrangement or square close packing arrangement. Whereas if I talk about the hexagonal close packing, then you can say that if this is y-axis and this is x-axis, then this is AB type of arrangement. If you see the second layer, the centers of the atoms of first layer and second layer does not coincide with each other, or we can say that the centers of atoms in second layer is not exactly above the centers of atoms in first layer. But as we go to third layer, the centers of atoms in third layer is exactly above the centers of atoms in first layer. That is why I have written A, B and then again A. Why? Because the centers of atoms in third layer is exactly above the centers of atoms in first layer, and similarly the centers of atoms in fourth layer is exactly above the centers of atoms in second layer. So it becomes AB type of arrangement or hexagonal close packing in 2 dimensions. Now let us talk about coordination number now. Coordination number. If suppose I choose this sphere or this atom, and I want to see how many spheres, different spheres this particular atom is touching, or how many spheres are in contact with this particular sphere, then if I choose these centers, I can say that since these are 4 corners, it means 4 different atoms or spheres are going to touch this particular chosen atom. Now since this particular chosen atom touches 4 different spheres at a time, it means the coordination number in square close packing becomes 4. Now if I talk about hexagonal close packing, and if suppose I have chosen this particular atom or sphere, okay, and I want to see how many spheres at a time it is going to touch, then I can say that if I choose these centers and join them, then I realize that there are 6 different corners. How? 1, 2, 3, 4, 5, 6. There are 6 different corners which are centers of each sphere. It means at a single point of time, this particular chosen sphere is going to touch 6 different spheres. It means coordination number in hexagonal close packing will be 6. Why? Because every single sphere is going to touch 6 different spheres at a time, and in square close packing every single sphere is going to touch only 4 different spheres at a time. So since the number of spheres a particular sphere is going to touch is coordination number, so coordination number in square close packing becomes 4 and coordination number in hexagonal close packing becomes 6.
Choose the right kindergarten, a right bag, and matching bottle to go with. The right school, the right friends. Choose the right subjects and score well. Be an expert in all. The right teacher, and make sure that they like you. Choose the right timing, the right bus, and take a cab if getting late. The right train, and don't stand near the gates. Mind the pockets. Better get into ladies' compartment. Make sure your mustache hasn't started coming. Choose the right study time and forget games. IPL, IHL, rock and metal, guitar, axe. The right group and be a model to your brother. Seriously. Choose the right syllabus, the right test paper. Keep guessing questions for exams. Choose the right branch, the right college, the right stream. Choose the right career. Lucky to have a father's business to take care of and a father to allow that. The right counselor, the right form, and make sure the project is submitted on time. Choose the right website and rely on your friends for more information. Oblivious of the sites they have been to, there is no end to your woes. Getting better with every step you climb up the ladder. The summer vacation shorter, the bucket list bigger, the night darker, the books heavier. The only light you have is your friends ahead of you. Probably he is right. Ever thought how he got the direction? No more spending your energy and money on coaching classes. No more missing classes for rain, rally, and nonsense. Get your interest back in subjects through our creative ways of teaching. Doubts, concepts, applications, all explained through one vibrant animation. Subjects covered by multiple teachers with repeat telecasts. Special programs only for basic foundation and paper analysis. Personality development, career counseling, admissions, hobbies, all covered. A new approach to study with long-term perspective. So sit back comfortably in your homes and watch Study Spectrum TV channel.
Now let us try and understand close packing in 3 dimensions. We have seen about close packing in 1 dimension. We have seen about close packing in 2 dimensions, that is square close packing or hexagonal close packing, correct? Coordination number in square close packing was coming out to be 4, since every sphere touches 4 different spheres, so coordination number was turning out to be 4. And in hexagonal close packing, coordination number was turning out to be 6. Why? Because every single sphere is touching 6 different spheres, correct? 6 different atoms. Now let us talk about close packing in 3 dimensions. Since we have introduced 2 different layers, one along x-axis and one along y-axis, it becomes 2 dimensional. Now we will try to place spheres in along z-axis, it will make packing in 3 dimensions. So close packing in 3 dimensions can be done in 2 ways. If I choose square close packing from 2 dimensions and try to build the 3rd dimension, then I can say close packing in 3 dimensions can be achieved also from 2-dimensional square close packed layers. If I choose square close packing of 2 dimensions and try to build the 3rd dimension, then it is one of the type of close packing in 3 dimensions. If I choose hexagonal close packing of 2 dimensions and try to build the 3rd layer along z-axis, then it is close packing in 3 dimensions using or from 2-dimensional hexagonal close packed layers, which is further classified. We will talk about that. So let us see about close packing in 3 dimensions by choosing 2-dimensional close packed layers. Then how it can look like. Suppose if I take the same spheres, if you remember, this single layer which you see is close packing in 1 dimension, correct? If I place another layer above it, then I am trying to build a layer along y-axis, and this becomes close packing in 2 dimensions, correct? Now suppose I already have this square close packing, correct? I already have this square close packing, which you can see the first layer which you see is along x-axis and the second layer which you see is along y-axis above it, correct? This is square close packing. If I place the same type of layer above it, correct, then you can see the center of each above sphere is in line with the center of each below sphere, and this becomes a 3-dimensional close packing from square close packed layers of 2 dimensions, correct? The above layer which you see, try and understand. This is x-axis, correct? This is x-axis. I have placed second layer above it. This is x-axis. I have placed the second layer above it, and it becomes y-axis. So this is square close packing, and it is only having 2 dimensions. The third layer along z-axis is still not visible. This is square close packing and only in 2 dimensions. Now suppose I introduce the third direction like this, correct? Then the center of the spheres in the third direction, that is z-axis, is exactly above the atoms or the spheres of this particular y-axis layers, correct? Like this. So it means if I try to build more number of spheres in 3 dimensions, the structure will look something like that. Now this is actually a type of structure, correct? This is the smallest part which can build from n number of spheres built over the 2-dimensional square closed packed layers. So this becomes a type of 3-dimensional closed packing structure. Now if I choose, suppose, hexagonal closed packed layers, closed packed layers. Now this is my close packing in 1 dimension, correct? This is my close packing in 1 dimension. If I place the second layer to build the second dimension like this, where the centers of second layer is not coinciding with the centers of atoms placed in first layer, or in other words, the centers of atoms of second layer is not exactly above the atoms of first layer, then it is hexagonal close packing, correct? Now if I choose hexagonal close packed layers and I have to place the third layer, there are 2 different ways which way I can place the third layer. Let us try and understand them. Now if you see this diagram of spheres, those spheres in green circles are 2-dimensional hexagonal close packed layers, and I am trying to place the third layer which has been drawn in purple color, that is the third layer. Now while doing so, by placing the second layer above the first layer, where the first layer is nothing but hexagonal close packed layers, then there forms 2 types of different voids or holes rather. Those are tetrahedral holes and octahedral holes. It means if I have this first layer of hexagonal close packed structure, which means this way, if you remember, this is the close packing in 1 dimension. If I place the second layer where the center of this atom of second layer is not exactly above the center of any of the atom of the first layer, like this, then these type of arrangement becomes hexagonal close packing structure, correct, of 2 dimensions. Now if I choose any three spheres of hexagonal close packed layer structure as the first layer, and if I am trying to place the second layer, and this is the atom of second layer, if this happens where the center of the atom of second layer is exactly above the hole of the first layer, then it forms a tetrahedral hole. The space between these 4 touching atoms of this particular structure, where 3 atoms belong to first layer and this 4th one belongs to the second layer, then the gap between these 4 touching spheres is exactly your tetrahedral hole. If you see this structure which has been taken out from this particular diagram, where the 3 green circles belong to first layer of hexagonal close packed structure, and the purple color circle, which is the 4th atom, belongs to the second layer, and we are trying to study the close packing in 3 dimensions by placing the second layer above the first layer, which is in form of hexagonal close packed structure, correct? So if I place this atom of second layer exactly above the void or hole of the first layer, then it forms a tetrahedral void. This gap, which if you join the centers of each sphere of this particular balls in my hand, then it will form like this, where these corners are nothing but the center of these three atoms of first layer, which is hexagonal close packed layer, and this particular center in purple color is this particular at the center, if you see, is exactly the center of this atom of second layer. So if I join the centers of each atom of this particular structure, then it becomes a tetrahedral hole. Now then, what is the difference between a tetrahedral hole and an octahedral hole? Let us understand that. Suppose if I take a particular case from this diagram, this one if you see over here, such that this is the three atoms of first layer, which is in form of hexagonal close packing, and these are three different atoms of second layer, such that they have been placed in this fashion. Correct? If you see, these three are the atoms of first layer, and these three are the atoms of second layer placed above the first layer, and first layer is in form of hexagonal close packing. Correct? Now if suppose I place these atoms of second layer in such a fashion where this type of void is forming. So you try and understand, these three atoms are not exactly above the centers of these three atoms of first layer. These atoms of second layer have centers above the gap between the two adjacent atoms of first layer, like this. Correct? If you see this particular diagram, the green circles, the green spheres are the atoms of first layer, and the purple spheres are the atoms of second layer. And when they are placed in such a fashion like this, where none of the centers are in a straight line, then the gap between them is actually your octahedral hole. This octahedral hole. Now if you join the centers of each atom of such a particular case, then it becomes an octahedron. This is octahedron, where all green corners are the atoms of first layer and all purple corners are the centers of atoms of second layer. Here in this case, tetrahedral hole case, this particular structure is called tetrahedron, and this particular structure is called octahedron, which has been formed by these 6 different spheres, 3 from first layer and 3 from second layer. Whereas if I have chosen only one atom from the second layer, then the gap between them is actually your tetrahedral hole. But if I choose 3 different atoms of second layer and I place in such a fashion that none of the centers coincides in a straight line, then straight vertical line, then the void or hole, the gap between them is your actually octahedral hole. And if you join the centers of each atoms in this particular structure, then it becomes an octahedron. Now do remember, if number of spheres in a closed packing of in 3 dimension is suppose represented by capital N, then number of octahedral voids will be exactly equal to the number of spheres, that is capital N, whereas number of tetrahedral voids will be exactly double of the number of spheres, that is 2 capital N, 2 into capital N, or 2N. So if there are n number of spheres in a closed packed structure in 3 dimension, then the number of octahedral voids will be exactly equal to the number of spheres. That is, if there are 10 spheres in 3D arrangement, 3-dimensional arrangements in such a fashion, then the number of octahedral voids formed will also be 10. But the number of tetrahedral voids formed will be 2 into 10, that is 20. That is why if number of spheres is represented by capital N, then number of octahedral voids formed will be exactly equal to the number of spheres, that is N, and number of tetrahedral voids formed will be twice of number of spheres, that is 2N. Now we have talked about what will be the case tetrahedral void or octahedral void formed if we place the second layer above the first layer, where the first layer is actually your hexagonal closed packed structure. We have talked about the second layer. Now what if we place the third layer above the second layer? Then there are two different possible cases. The first possible case is covering tetrahedral voids. Now if you remember, this is a tetrahedral void, the void formed by these four spheres, where the bottom three spheres are actually the atoms or the spheres of first layer, and the above this particular atom is the atom or sphere of second layer. Correct? Now the first case is covering tetrahedral void. Now what if this is also a tetrahedral void? You can see this is also a tetrahedral void, correct? Exactly above the first tetrahedral structure, like this fashion, then you can see that the spheres, these three spheres, the centers of these three spheres are now exactly in line with the centers of bottom three spheres. If you see this centers of atoms of third layer, this is the first layer, this single atom placed above it is the second layer, and these three are the third layer, and above it is fourth layer. So if I cover this tetrahedral void like this, you can see that the center of the atoms or spheres in third layer is now in exactly line with the centers of the atoms of the first layer. These three are in third layer, and the lower ones are in first layer, the above one is in second layer. Now if I place this particular third layer to cover the tetrahedral void, then I can see that the center of these spheres in third layer is now exactly above the centers of spheres in first layer, correct? So this is the first case where we can say that covering tetrahedral void by placing the third layer above the second layer. Now the second way of placing the third layer above the second layer is covering octahedral voids. Now we have seen that if these are the atoms of first layer, and if these are the atoms in my right hand, if these are the atoms of second layer, if I place these atoms in this way, then it forms an octahedral void. Now we have talked the first way of placing the third layer above the second layer for covering tetrahedral voids, and we have found that the centers of the spheres in third layer was exactly above the centers of spheres in first layer. That is why we can say it is AB type of structure, correct? Now we are trying to cover the octahedral void. Now this is an octahedral void, correct? This is an octahedral void. Now I want to cover this octahedral void. You can see the centers of atoms or spheres of second layer are not exactly above the centers of spheres in first layer, correct? Now if I want to cover this octahedral void, I am placing this third layer, correct, in order to cover this octahedral void. Now the moment I place this sphere to cover the octahedral void, I found that the centers of the spheres of first layer, the centers of spheres of the second layer, and the center of the sphere in the third layer, none of them are in a single straight line, in a single straight vertical line. It means the centers of the spheres in second layer are not exactly above the centers of spheres in first layer. The center of the sphere in third layer is not exactly above the center of sphere in second layer, and also the center of sphere in first layer. So we can say that this is A, B, C, and after that again the fourth layer will have A type of structure. Why? Because the fourth layer, when we try to place the fourth layer, the spheres in the fourth layer, the centers of those spheres in fourth layer will be exactly above the centers of spheres in first layer. So this becomes first layer A, second layer B, and third layer C. Whereas in case of tetrahedral, for covering tetrahedral void, we were getting AB type. Why? Because the centers of sphere in third layer was coming out to be exactly above the centers of spheres in first layer. Whereas here to cover octahedral void, we are not getting such type of case. We are getting three different layers where none of the centers are coming in a straight vertical line. But if you place the fourth layer, then the centers of spheres in fourth layer will be exactly above the centers of sphere in first layer. So this is first layer A, second layer B, third layer C. Fourth layer will be again A, and then fifth will be B, and sixth will be C. So this is A, B, C, A, B, C type. That is why if you see over here I have written green, in green A, white B, and in purple C, and again the fourth layer will be A type. Why? Because the center of spheres in fourth layer will be now exactly above the centers of sphere in first layer. So this is the way where we can place the third layer in two different ways, by covering the tetrahedral void first case and by covering the octahedral void the second case. Correct? Do remember, in case of tetrahedral void, the third layer is exactly the same as first layer. That is why it is AB type. Whereas in case of covering octahedral voids by placing the third layer above second layer, then in that case we have ABC type. Why? Because the centers of spheres of the fourth layer will be exactly above to the centers of spheres in first layer. So this is ABC type.